weekly contest. Problem number 2273, find resultant array after removing anagrams. So we are giving an array words where all of this contains lowercase English letters. So like this is one of the member of words. In one operation, we can select any index I within the words when words I need -1, so the index just before it, and words I, the one that is represented by the index I we chose, are anagrams, then we will delete the words I from the words, keeping performing this operation as long as we can. Select it that satisfies this condition. Now, what is anagrams? Anagrams is a word phrase formed by rearranging the letters of a different word or phrase using all original letters exactly once. So it means that it contains all the letters. So two things are anagram when they have the same letters, and they are still considered anagram regardless of the orders of the letter. So if it has 2A and 2B, this also have 2A and 2B, and that's it. This is anagram regardless of the orders of the letter. So that is anagram. Now return words. So this is the args of the function we need to write. Return the words after performing all operations. So basically we do deletions for its index that is an anagram of its previous one. So for example, in example 1, ABB, this is the original words. It ends up output like this. The process is first, Baba is this index is having anagram with the previous one, so we have deleted. We will delete this index. So after deleting this index, it will okay, maybe we will just follow the order here so it will be easier to explain. So in the order here, they start with this one. They start with this one and they check that it is the previous index of this is BABA, and that is an anagram. Then what happened is we delete this. So now after deleting this, we are left with these words. You see that the BBAA are gone. Okay, then after that we continue on with these words. So BABA now is the one being checked, and we can check that it is the previous index is an anagram of BABA. So in that case, we will remove BABA and we will left with this. And after that, they tried with this one, where the previous index is an anagram of itself. It even this exact same things. So we will delete this one, and that's it. While for this one, if you can see, all these contains unique characters, unique letters. So there is no anagram with each other, so the output is the same thing. Okay, so that's about the problem, and we can see that everything contain at least one letter, and we will always have at least one. Everything contains at least one letter, maximum of 10, and the total problems is at least one, maximum of hundreds. So the question is how to solve this. So that's the problem. Now let's talk about the tactic. Okay, so there are two key points here. First is the definitions of anagram, right, where we can say something is an anagram as long as they have the same number, the same letters regardless of orders. So in this case, we can say that an anagram is when they have the same letter and each letter they have the same frequencies of occurrence. So in this case, for example, ABBA and BBA are anagrams because they have A and B, and they have 2A, exactly 2A, same 2A, and same 2B. So that's an anagram. The second key point here is about the operations. That the operations requires that the anagram relationship is happening between itself, the one that we are asking whether we should delete or not, with the previous index. So that's it. That's the thing. And from that on, after understanding those two, one way we can think about it is because it has a relationship that about the previous one, we should start from index 1. We can make it an order in orderly fashion by starting with index 1, and then we do the check whether we should do the operation there. If we have to do the operation there, then we will do the operations. Remember that at the end we have to return the last point, right? After we do the operation, what is next? Let's say in this case BABA is having anagram with the previous one, so we have to delete BABA. Now after deleting this, what else we need to do, right? The next thing we need to do, of course, if this is to be deleted, we go to the next one. And then the next one will do a check to the anagram. But remember that we have deleted this. It means if we have deleted this, the next one will have to check this one as the previous, because after deletion it is compacted. Remember that. The words become, the next words become the words without the BABA. So at that time, this one should be compared with this, and so forth. Let's try to put it in writing, run it a bit, what I really mean by that. So for example, from here, we will start with index 1, right? And index 1, we check, we do the check. Is BABA, the previous one is the anagram? Yes, it is. When it is the anagram, what we do is we delete this. And because this is a list, of course, it's not as easy as do deletion that representing things like this in Python, right? Because it means we need to move all the previous things into the what do you call that? Into the index -1, which is expensive. It means for each deletion, we might need to do a big O(n). So we have to symbolize this, symbolizing the deletion to make it simple. Okay, after we do the deletion here, we mark it as none. Then what happened is we move to the next index to check. And then the next index, it will check the previous one. And how does it find the previous one? Is it won't be just a simple -1, because this could happen, right? So what happened is the previous one of BBAA after any operation before, involving any operation before, is to find the first not none. That will be the previous index of BBAA. So the first not none will be this. And we can see that these two are anagrams. So now we delete these two. Then we move to the next index, 3. Now for this one, we will check the previous one. And once again, because we use this modified list to actually efficiently representing the deletion mark in the words, we need to find the first none. And that would be this, right? And we can see that this is definitely not an anagram pairs. So we don't delete this. Then we move to the next part. The next part will be here, CD. And then we will check the previous one. The previous one is this, right? And that would means that we need to delete this. Okay, then after these deletions, that's about it. That's about it. And then that's it. Now, one thing to be noticed also, what happened if it was comes down, just now before we do the last part, right, it becomes this. What happens if this is not an anagram, right? So when we reach this part and we check the previous one and it is not uh, an anagram, then that's it, we also left it out. And after I actually going over the budget, the length of the list, then we have done the things. And after that, we can just tidy up for the final result, which final result will just be, let's remove this to avoid confusion, will just be this. Now, this will work always because if it needs to delete, it will delete itself. So there is nothing else need to be done. If it is not an anagram, it will not delete itself. So all this one-time scanning works. Okay. Now let's. That's basically the tactic. So the tactic is first understanding what an anagram is. Make it a definition that you can write code with and as efficient as possible, which is just now we say it's the frequencies of all the letters possible. And the second one is about the check. The check will start from index 1 and going for each check, and if it is the anagram, we delete it, but we don't literally delete it, we just mark it as none. After we do that, we will compact it down and then return the result. Okay. Now let's write the code. First is the definitions. So basically, we will convert all the words there into the definition we just mentioned. Okay. So this conversion of word is basically about what we say just now. So first we need a counter map, and then what happens is for a character in each of the word, we will put a counting into it. Okay. So this is basically if the character is not yet in our map, counter map, we will start it with 0. Otherwise, we will increase the number by 1. After that, we can do the check. One of the thing about the dictionary, it doesn't guarantees about the order. So in order to make sure we have a guarantee of order, why we want to have a guarantee of order, this is just another way to say to make sure that we match, we check all the characters possible, right? So we will have to get the keys in order. So we sort it, and after that, what we need to do is actually we need to create an ordered counter, basically a simple list, and then for each key in keys, which is a sorted one already, we will do ordered counter dot append two things. First is the key itself, which represent the letter actually, and also the counter. After this, we will just convert it into a string. So now anything that have the same value of what was converted means they are anagrams. Okay, because now what we do here is we convert each word into ordered list of letter and its frequency, and that will be the same for things that are anagrams. And to make it also less recalculation, we can do a catch here. Okay, So what happened is we will catch it. Let's say conversion catch. When for the word, no, it doesn't matter. Unless we have a lot of, what you call that? Unless we have a lot of things with the same word, actually this doesn't really matter. We can just do this. So if we know that the traffic will have all the same letters in the future, we might want to do that catching to actually save a bit. But for now, let's just do it like this. Okay. So after we have these anagram definitions, we can we will convert each word into its converted one in order of it. So that's about it. Actually, this one should be dot append. Now we have a list of things to later on check whether it is an anagram or not. So now we have solved one problem part, which is the anagram definition. Next, we will implement this, which is about the checks. Okay. So for I, we now will use index because we want to exactly override the values if it is supposedly to be deleted. Okay, so we now, for each I, remember we will start from 1 because the relationship for the operation requires there is something in the previous one. Okay, so what happened is the offset, of course, will be negative 1 before it, right? And the check is if words, we will check for the anagram. Anagram, remember, we define it into the conversion words. So what happened is I minus 1 equal to convert words of I. But because later on we will do this kind of non-marking, we can't really say -1, we have to say offset. Okay. If it is an anagram, then what happens is we will make the words into none. And what is the right offset? The right offset needs to be searched. While words I minus offset is none, then we will increase the offset. Okay. Of course, we also need to check if this is not over the boundary. So I minus offset should always be bigger than 1, than 0. So if we can find it, it will keep increasing. If not, then that's it. And then after we find the offset, we will check for the anagram. If it is the anagram, then we actually going to put a none on it. Okay. Then after that, word size is none. This should already did what we are doing here. And then what happened is we need to return the final result, the resultant array, which is if word is not none, this is when we append it to the final result. And after that, we just return the result. Okay, So let's run this. Looks like it's good. Let's use all the sample cases available. Yep, it working fine. Now let's submit it. Yep, it's correct. So to summarize again, the implementation first is with tackling the anagram definition problems, which is by converting it into an ordered list of letters and its frequency. And then after we have that, we just do the things, the operations. But one thing to be noticed that we need to keep track of offset. So -1 not always going to be the offset, because when we say we do delete the words, which is the operation required, what we do in the Python list is actually we mark it as none. So the position index will still be there. That's why offset will not always be -1, but we need to actually track what is the offset for it by checking whether it is none or not. If it is none, then we move on, move on, and move on. If it is not none, that's when we actually starting. Okay, so after that, we actually going to filter out the result into only the one that is not none, and then we return it as our solution. Now, how about the time complexity? The time complexity for this, first is the conversion. The conversion going through for C in words, so that will be N, right? That will be, what you call it? It actually will be a constant because at maximum it's a 10 words. And then keys, here are the counter keys. So that basically is as much as what the character is, and then we sort it, and for each letter, this is all our big O 10. Okay, it's because the knowledge of the constants we know that at maximum it's 10 characters only, big O 10. So that's about its relationship with the letters. How about the conversion itself? This is as much as the word can be done. So this will be big O N, of course. Okay, and then this for each of the word, so this is definitely a big O N. Now we check the inside. For each of this, the offset is, it could be doing an offset here, of course. Then what needs to be done here is actually, this could be at most actually another n, right? At most another n. And then if convert is done, so this is become n squared actually. Now can we make this lesser than n squared? Because if we notice that once it's got into none, the next one definitely no need to check this. We actually can trace it, that the first, what will be the first not none in the what you call it, in the list, right? Though in this case actually even we do n squared, it's it's actually accepted. So the performance is good enough for the problem. But in case you want to make this more efficient, an idea here is actually once it's got into none, then we will know that the next previous not none will be something like this, right? Something this. So what happened is, rather than tracking, not only tracking it into none, but we can also track with the first prev not none index. Okay, so we can track it this. So what happened is, for the next one, when we go to the next one, rather than checking whether it's none or not, we can directly jump into the first not none that we knew about, which of course it will always be the index just before this, right? So for this one, for example, then the first brief not none index will be I minus offset, for example, like that. Okay, this one, of course, the first one will be 0 when we are doing starting from 1, and then starting from 1, the first one is 0. Then what happened is the first previous index of it will replace this. Okay, and then after that we no longer need the offset things. So what happened is it will always go to check this one. If it is the same, then we do the revisions, right? If it is not, then the first brief not none index will actually be the index itself. So this will make this into big O(n), because now we just need to track the first previous not none index. It will always start from 0 because we start from the first index. And then if it is an anagram, we make it into none, and the first previous index will be the one just before it. So actually it will stay the same when it is none. So we don't need to do anything. But if it's not becoming none, the new index that we just check for anagram become the replacements of it. Okay, so let's see if this works. Wait, well, okay, yep, seems like it's correct. Let's submit this, and it's correct. So this is the big O(n) solutions. So now tracking it like this will make it big O(n), and then forwards in words, of course this is big O(n) because we filter it one by one. Now after we got its component of it, what is the big O? Everything is big O(n) and it is sequential, so we just sum it up. When this is being summed up, all of this will means that the time complexity is big O(n) for this solution. So remember this more efficiency we introduced by just tracking the first previous not none, nothing in the pattern. Although the previous n squared worked, but this one definitely is more efficient. So that's about it for this solution, for these problems. So not only we talk about one solution that is straightforward using the none, and then we also optimize it into big O(n) by tracking just the first previous not none index. So that's about it. Hopefully this is useful. Thank you.